Hello students, welcome back to your online video classes. So in the previous class we have started our new chapter electric current. So electric current is charge flowing per unit time, that is charge divided by time, that is I is equal to Q by T. The unit of current is ampere. There are smaller units of current, that is milliampere and microampere. Milliampere is 10 to the power minus 3 ampere and microampere is 10 to the power minus 6 ampere. Then we discussed an example 1 in which we have to calculate the number of electrons flowing. Then we discussed the potential difference, the actual reason of flowing current, like temperature difference for heat current. Then we studied the various symbols which we will use in the circuits like ammeter, voltmeter, rheostat. Then we started the Ohm's law and the experimental verification of Ohm's law, that is V is directly proportional to I and the graph of I versus V is a straight line. Then we discussed the resistance, that is the restriction of flowing electrons. So then we discussed the dependence of resistance. The various dependencies are that R is directly proportional to length, inversely proportional to the area of cross section, and in conductors, semiconductors and insulators, they are variously depending on the temperature. Then we discuss the dependence of resistance on the materials and the order given between the aluminium, gold, copper and silver. Then we started the combination of resistances, that is first of all series combination, in which we studied that the value of current is same and potential difference is different for various resistances. Then we solved the example 4 regarding the series resistance. Now today we will start the parallel combination, in which potential difference will be same, that is every resistance which are connected in the circuit are between the 2 points A and B. So potential difference will be same and current will be different according to the values of resistances. If resistance is more, then current will be less, as restriction of flowing is more. So you can say that resistances are connected between the same points A and B. So their potential difference will be same and current will be different according to resistances. So I1 will be according to the Ohm's law V by R1, R2 is equal to V by R2 and I3 is equal to V by R3. So by adding all these I1, I2 and I3, you get the total current I. So the total current of the circuit will be V by R equivalent and this will be equal to the V by R1 plus V by R2 and V by R3. So by that you get the parallel combination formula of R equivalent, that is the total resistance of the circuit, that is 1 by R equivalent is equal to 1 by R1, 1 by R2 and 1 by R3. So if only two resistances are connected, then you can convert it into a simpler form, or you can say a formula for direct use, that is 1 by R1 plus 1 by R2 by taking the LCM, that is the product of R1 and R2, and then you get the R equivalent is equal to R1 R2 divided by R1 plus R2. So regarding the parallel combination, there is an example, that is example 5. The question is 3 resistances of 1 ohm, 2 ohm and 3 ohm are connected in parallel in an electrical circuit. If this circuit is connected with a battery of 6 volt, then you have to find the following. First of all, the A part is equivalent resistance of the combination. B part is current in the circuit. C is current in each resistance. So you have to find R equivalent of the whole parallel combination. So you will use the formula of parallel combination. Then by putting the values of R1, R2 and R3 and taking the LCM of 1, 2 and 3, that is 6, you will get the R equivalent, which is equal to 6 by 11 ohm. Then in the B part you have to calculate the current of whole circuit. So in B part the formula will be V by R equivalent, the potential difference of the whole circuit, that is 6 volt, and the R equivalent, that is the resistance of whole circuit, that is 6 by 11 ohm. Then current will be 11 ampere. Then in the C part you have to calculate the each value of the current in every resistance. So first of all in I1 you will have to take the value of R1, that is 1 ohm. So I1 is equal to V by R1 and V is 6 ohm, R1 is 1 ohm, then you will get I1 is equal to 6 ampere. Like that you can calculate the values of I2 and I3 as well by putting the values of R2 and R3. So this was example 5. Now we will discuss example 6. Question is, find the equivalent resistance between A and B in the given circuit. So in the circuit, first of all, three resistances of equal value 2 ohm are connected in the parallel combination, and the second one again the three are connected in the parallel combination, and then they both parallel combinations are in series with 2 ohm. So first of all you will have to calculate the values of parallel combination and then the overall series combination. So first of all we calculated the parallel combination by formula 1 by R equivalent is equal to 1 by R1 plus 1 by R2 and 1 by R3. By that we get R equivalent 2 by 3 ohm. So the values of resistance are same in the next one, then the R equivalent will be again 2 by 3 ohm. Then they both are in series with 2 ohm. Then R series will be 2 by 3 plus 2 and plus 2 by 3. Then it will be 10 by 3 ohm. This was the example 6 regarding the parallel combination. Now our next discussion is about thermal effect of current. In thermal effect, when we provide chemical energy of battery to the circuit, then this will allow the flow of electrons in the conducting wire. That means the chemical energy is converting into the kinetic energy. But now this kinetic energy of electron will convert into the heating effect by colliding with the atoms present in the conducting wire. So by that collision, this kinetic energy is converted into the heat energy. So at last, if only pure resistance circuit is connected, then the chemical energy of battery is converted into the thermal energy of the circuit. So the formulas of this heat energy will start with the work done. The work done by charges for flowing between the potential differences. So work done will be equal to the charge flown and the potential difference, that is QV. You can write Q that is equal to IT as Q is equal to IT. As I is Q by T, then Q will be IT and V is IR by the Ohm's law. Then we will get the work done is equal to I square RT. So by that you can say that heat produced is directly proportional to the I square and directly proportional to the resistance of circuit, as well as the heat produced is directly proportional to the time taken. This law is known as law of Joule heating. So the formula of heat produced will be I square RT. Now the next term will be the electric power, that is the electric energy produced in unit time. The unit will be joule per second or watt. The 1 kilowatt is equal to 1000 volt. The kilowatt is the greater unit than the watt. In practical use, we will use the kilowatt and hour units because they are very convenient for the calculation. One more practical unit which is commonly used in the terms of power is 1 horsepower. 1 horsepower is equal to 746 watt. So these were the units of electric power and electric current. The thermal effect of current includes that the chemical energy of battery is converted into the thermal energy of conductor. So by the flowing of, you can easily observe in the practical use, like the continuously running fan will have a higher temperature. Like that we will use the electric heater, electric press and electric geysers. So these were the units, but in the hours, the time taken will be in 1 hour. So 1 hour will be converted into the second, that is 3600 second, and kilowatt is 1000 watt. So by that you can convert the kilowatt hour into the joules, and these were the relations of electric power and electric energy. By the interconversion you can calculate these terms. So chemical energy of battery is finally converted into the thermal energy. Now we will discuss the question 7. In example 7, the question is, a 10 volt storage cell is connected to a nichrome resistance coil of 50 ohm so that current flows for 1 hour. So time given is 1 hour. Calculate the heat generated in the resistance. So we have studied the formula of heat resistance is I square RT. By that V is given, that is 10 volt, and R is 50 ohm. So current will be V by R, that is 1 by 5 ampere, and time is 3600 seconds. So by the formula heat generated is equal to I square RT, then you get the answer 7200 joule. Next question is example 8. An electric bulb is connected to a source of 220 volt and the current flowing through the circuit is 0.5 ampere. What will be the power of the bulb? Power is VI. V is 220 volt and I is 0.5 ampere. So power is VI. Then by multiplying 220 and 2.5 you will get the 110 and the unit of power will be watt. So these were the questions which are related to the thermal effect of current and electrical heat and electric power. After that, now we will start the discussion of magnetic effect of current. The scientist Ørsted started this discussion when current flows in a conducting wire. Then in the surrounding, magnetic field is produced which is measured or detected by a compass needle. So this was an accidental discovery in which he was flowing a current in a conducting wire and a magnetic needle was accidentally placed near it. Then he observes a slight deflection in the magnetic compass needle. So then he concluded that by flowing the current in a conducting wire, magnetic field is produced near the surrounding area, and if you place the compass nearer to the conducting wire, then it will deflect more, and if you are taking it away, then it will deflect less. If you are changing the direction of current, then the direction of deflection will be changed. So the three laws or observations which are given by the Ørsted scientist regarding the magnetic effect of current are: first of all, when there is no current flowing through the conductor, then magnetic field is not produced around the conductor and the magnetic needle will not deflect. Second one is, when current flows through the conductor, then magnetic field is produced around the conductor and it is detected by the needle. Third one is, if you are changing the direction of the current, then the direction of deflection will also get changed. These were the observations made by the scientist Ørsted. Then there is one more discussion about the direction of magnetic field. Two rules basically used for detecting the direction of current and direction of magnetic field is, first of all, the right-handed corkscrew law, in which you have to rotate a screw. So the rotating direction will be the direction of magnetic field and the growing upwards or growing downwards of the screw will be the direction of current. Like that, there is a right hand law in which the curled fingers will denote the direction of magnetic field and the thumb going upwards or downwards will denote the direction of current. So these are the laws basically for knowing the direction of magnetic field. So these magnetic fields are expressed as that there is a magnetic pole, south pole and north pole. These are the imaginary poles which you are using for the study purpose. These are made according to the direction of magnetic field. If the magnetic lines are moving outwards from the magnet, then that pole is north pole, and if magnetic fields are entering, then the entering pole will be the south pole. So this is the magnetic field and the magnetic field lines which are imaginary. If magnetic fields are very nearer to each other, that is near to the poles, then the strength of magnetic field will be more. If magnetic fields are at a farther distance from each other, then it denotes that the intensity of magnetic field is less.